Okay, perfect. So, welcome everybody to the first AJS seminar of 2021. Today we have with us Giuliano Klun, that is a last year PhD student in CISA under the supervision of Professor Fonda. And he will talk about well-ordered and non-well-ordered lower and upper solutions for periodic planar systems.
Good morning to everybody. Good afternoon. And as Manuele said, today I will speak about my last work with Professor Fonda and Andreas Fecci, whose title is Well-ordered and Non-well-ordered Lower and Upper Solutions for Periodic Planar Systems. Let me start by recalling some standard definition for second order scalar periodic problem of this form x prime prime equals g with periodic condition at the boundary of the interval 0t. And let me recall the notion of lower and upper solutions for this kind of problems. Alpha from 0t to in R of class C2 is a lower solution of the problem if this inequality holds for the second derivative of alpha with respect to g, and alpha has this property at the end of the boundary of the interval 0t, namely alpha of 0 equals alpha of t, and alpha prime of 0 is greater or equal than alpha prime of t, while beta from 0t in R of class C2 is an upper solution for the problem if the reverse inequality holds for beta prime prime with respect to g calculated in t, beta of t and beta prime of t, with symmetric conditions on beta and beta prime at the boundary of the interval 0t. So today we deal with the following periodic problem of the form x prime equals f of t, x and y, and y prime equals g of t, x and y, with periodic condition at the boundary of the interval 0t. And here we suppose that f and g are continuous functions, capital T periodic in the variable t. The goal is to find the theorem of existence of solution of this kind of problems in the case of well-ordered and non-well-ordered lower and upper solutions. More precisely, in this setting, we take a more general definition of lower upper solution for this kind of problems, namely alpha from R to R of class C1 and capital T periodic. We say that this is a lower solution for the problem P if there exists a unique C1 function that we call y alpha from R to R, such that this couple of inequality holds for f with respect to alpha prime, and this inequality holds for y prime alpha with respect to g calculated in t, alpha of t, and y alpha of t. On the other side, beta is said to be an upper solution for the problem P if the same condition holds for f with respect to beta prime, but the reverse inequality holds for y prime beta of t with respect to g. So for the first part, we will consider the well-ordered case, namely the case in which alpha is less or equal than beta. The first existence result we have found for in the case of well-ordered lower and upper solution reads as follows. Suppose that there exists a well-ordered couple of lower-upper solution of the problem P, and if we set capital A and capital B to be respectively the minimum and the maximum of alpha and beta, and we suppose clearly that capital A is less than capital B, we have to suppose that there exist two C1 functions that we call gamma plus and minus, defined on the interval A, capital B in R, such that this condition holds. This picture is a picture taken at fixed time, and the arrows represent the hypothesis on the field associated to the problem on the vertical boundary of a suitable strip, that is the vertical strip delimited by alpha of t and beta of t, and on the boundary represented by the curves gamma plus and gamma minus. With some details, we can enter now in details to make explicit this hypothesis, and we have to suppose that these two functions, gamma plus and gamma minus, are greater, gamma minus are less than the infimum of y alpha and y beta, and gamma plus has to be greater than the sup of y alpha and y beta. And moreover, G, this inequality for G with respect to the product F times gamma prime has to hold for every T in R and every X in alpha of T, beta of T. And this is the conditions we have to request on the boundary, and it is represented by the arrows starting on the curves gamma plus and gamma minus on the boundary of V. In this hypothesis, then there exists at least one solution of the problem P that remains bounded for every T in X between alpha of T and beta of T, and in Y between gamma minus of X of T and gamma plus of X of T. Now, the proof of this first existence result is rather technical, but I want to show you the main steps to achieve this result. Excuse me. We have to interpolate the field with a constant one on a vertical strip, that is the strip we have seen before. And we have to introduce a new problem that we call P tilde of the same type, but with different function f and g that we call f tilde and g tilde, that are of the following type. F and g are respectively y plus a function p, and g tilde is x plus a function q, and p and q are globally bounded. We show that with this interpolation, alpha and beta remains a well-ordered pair of lower-upper solution for the problem P tilde. Now, here is another sketch for at fixed time of the phase plane. And here, with a geographical, I can say, inspiration, the space outside the strip containing V, that is the white strip here containing V, has to be divided in 4 regions delimited by y alpha and y beta that we call with a geographical analog A and E, that stands for northeast because it is the upper right part of the phase plane, A southeast, that is the yellow region, the A southwest, that is the reddish pink region, and A northwest, that is the violet region. The second step is to prove that these four sets are pairwise invariant, and pairwise invariant in the past and invariant in the future. Namely, A northwest and A southeast are invariant in the past, namely if the trajectory for some times belongs to these regions, namely for t less than t0, the trajectory remains bounded in this region for every t less or equal than t0, and vice versa for A northeast and A southwest, in which if the trajectory for some time t belongs to these regions, then for t greater than t0, the solution remains in this region for every t greater than t0. So the last step is to invoke a topological degree arguments. Namely, we can introduce two operators, the operator L from the space of continuous function of C1 function periodic of period t to C0 function of period t, such that Lu is equal to U prime, that is the derivative component by component, and N tilde is the operator from C0t to C0t that associate to U of t, F tilde of t, U of t, and G tilde of t, U of t. Clearly, P tilde can be rewritten as Lu minus N tilde U equals 0. And now the goal is to define an homotopy that bring the problem P tilde to the much simpler problem x prime equal y and y prime equal x. And this is done simply multiplying by a parameter lambda, p and q, and define this homotopy for lambda between 0 and 1. Clearly, for lambda equals 0, we have the problem x prime equal y and y prime equal x. And for lambda equals 1, we have the problem P tilde. So in this case, we can use the coincident degree in a theorem by Capieto, Mawen, and Zanolin that allows us, once setting g, the function from R2 to R2 that associate to x, y, and yx, to say that the degree of the map L minus N tilde with respect to the ball dr of the functions, the continuous functions that have images bounded by the circle of a radius r centered at the origin is equal to the degree of the map G with respect to the ball of R2 centered at the origin and of a radius R. But this degree is nothing but the determinant of the matrix associated to the linear, in this case, transformation that maps x to y and y to x, and this is -1. So we have found a solution of P tilde because the degree is not 0. But this solution of P tilde is also a solution of P because we are able to prove that the solution we have found remains bounded in the region on which the problem has not been modified. Now, before passing to treat the non-well-ordered case, I have to make some remarks. Here, the notion of lower and upper solution can be generalized to the case when alpha prime and y alpha and respectively beta prime and y beta are piecewise continuous. This allows to recover some classical result for second order scalar second order equation when we can glue lower and upper solution defined on an interval on to extend them to all R by gluing copies of this function, but this may create a non-smooth solution. Here, the proof is very similar, but if you remember the previous image where four zones are defined, and let me return to this picture. In the case in which these functions are only continuous, the two lines y alpha and y beta becomes two half strip that and not a line that we call A east and A west, and we have to assure that this condition on the field remains valid not only on a line as here, but on all the point of the boundary of these strips. But the result is achieved analogously. Only one more curiosity is that this result is based on a previous result we have found in a previous article with Professor Fonda and me of the Poincaré-Bold theorem, when we have proved a theorem on lim-sup and lim-inf on the Dini derivative of continuous functions. Only to show that this works, although in a strange manner, are related in an unexpected way. Only one more remarks for this part, that we can also consider this kind of problem where phi is an increasing homomorphism mapping 0 to 0. And if we have a lower solution alpha for this kind of periodic problem in the classical sense, we can make a substitution, namely y equals phi of x prime, and we can set f to be the inverse of phi and g to be h of t x and y, and phi to the -1 of y. And here, if we choose y alpha to be phi of alpha prime, this meets all the requirements to be a lower solution in the broader sense we have defined it before, because this chain of inequality holds for f with respect to alpha prime, but not only, also of phi of alpha prime with respect to h. So this is a natural choice for solve this problem in the setting we have set before. And analogously, we can consider also y beta. And if we define y beta to be phi of beta prime of t, this meets all the requirement to be an upper solution. Now, the second part is devoted to the non-well-ordered case. Here, an analogous result can be set, but with two more hypotheses. One very similar to the previous one, but one far different. So we still consider the same problem, but now in presence of a non-well-ordered couple of lower and upper solution of P, namely the two lower and upper solution has a point T0 and 0T such that alpha of T0 hat is greater than beta of T0 hat. And we have to assume that f and g are bounded or controlled more precisely, but by two functions, namely f has to be bounded by a function key, a positive function key, times 1 plus the absolute value of x, and g has to be bounded by m times 1 plus the absolute value of y. And this uniformly on all the domain. Moreover, here the hypothesis is very similar to the previous one. We have that if we set a of t to be the minimum between alpha of t and beta of t, and b to be the maximum between the two, and we set capital A and capital B to be the minimum of A and the maximum of B, we have to suppose that there exists two functions, two family here of function gamma plus and gamma minus, depending on the parameter lambda that varies in the set 1 plus infinity, such that these two family are globally C0 and C1 with respect to the first variable, namely the variable x, and they tend uniformly to plus and minus infinity for the parameter lambda that tends to plus infinity, and this has to be uniform with respect to every x in the interval capital A, capital B. Moreover, we have to assure the same inequality for g along this curve with respect to f times gamma prime. But here, this inequality is not sufficient to request this inequality to be valid for every x in alpha of t, beta of t, because they are not well ordered. So this makes no sense as an interval alpha of t, beta of t. I don't know if alpha of t is greater or less than beta of t. But more surprisingly, it's not necessary to request that this inequality holds for every x between capital A and capital B. It is somehow an intermediate case. The situation again is this. And now we have three regions, the pink reddish regions below, the central region in blue, and the upper region in green, delimited by a pair of curves, gamma plus and gamma minus, for sufficiently big parameter lambda, and in x between a of t and b of t. Excuse me. And here again, with a geographical analog, we call the green region n lambda to stay by north, the central region, the C lambda, the region in blue, and S lambda, the south region in red, pink, reddish zone. So we can state our existence result that is the following. Assume the existence of a non-well-ordered couple of lower upper solution for P. If H1 and H2 holds, then there exists at least one solution of the problem P, such that the x component is less than alpha in a point, and the x component is greater than beta in a point T2. So again, we can give an idea, a sketch of the proof. So we are looking for solutions of the problem that remains bounded in this strip, and for lambda sufficiently large, as I have seen before, we can introduce the set n lambda, c lambda, and s lambda as follows. So this is the same picture with the names of the regions. And so we can prove that if U is a solution of P that touches the central zone for a certain times T equals T0, then the entire solutions remains bounded in a sufficiently big square centered at the origin for every T. Now, for this outside of Q, we can modify the problem P to obtain a new problem P tilde that is obtained again by suitably modify the problem to a new problem with the same characteristic as before. And we can prove that for this modified problem, the same a priori bound is valid. Moreover, we have that if U is a solution of P tilde belonging to the strip, then there exists a point such that the trajectory belongs to the central region for some time. So, recalling the definition of the zone of the strip S, we have that every solution of P tilde intersects C lambda. And we are able to prove that the two pairs alpha hat and beta hat constant functions and alpha and beta are lower upper pair of lower upper solution of P tilde, and we can prove after that these are well ordered lower and upper solution for the problem. And more interestingly, but here the proof is very technical, we can establish that there must exist two C1 functions, capital gamma plus and minus, defined between alpha hat and beta hat, such that the standard inequality we have seen before holds for G with respect for G tilde with respect to the product of F tilde times capital gamma prime. Now, with the existence of these two functions, we are able, and there is hope to apply the previous theorem to this new theorem, to this case, because we have pairs of well-ordered lower and upper solution, and we have found the function capital gamma that plays the same role of the gamma plus and gamma minus small in the first theorem. The situation in the phase plane is the following. With the low and with the two function capital gamma plus and capital gamma minus, the square Q and the direction of the field in the most important points. So we can define three sets U1, U2, and U3 as the sets defined in Y delimited by gamma plus and gamma minus, and in X delimited by the three couple alpha hat, beta hat, alpha hat, and beta of T, alpha of T, and beta hat. Clearly, for the position made before, U2 and U3 are contained in U1, and each of these three couples, alpha hat, alpha hat, and alpha and beta hat are well-ordered couple of lower upper solution. So we can apply the previous theorem. And again, we want to apply the previous theorem and to make a reasoning based on the degree theory. So we define for the three set U1, U2, and U3, three set of functions that are the functions in C0t, such that the trajectory Tu of t belongs to U1, U2, and U3 for every t. And we define a fourth set, calligraphic U4, as U1 minus the union of the closure of U2 and U3 calligraphic. So we can prove that U4 is nothing but the space of the continuous function periodic of period capital T, such that the pair U of t belongs to U1, clearly, but more interestingly, there exists T1 and T2 in 0t, such that x of T1 is less than alpha of T1 and x of T2 is greater than beta of T2, and this is contained in the strip. So we prove that there are no solution of P tilde on the boundary of U1. So the degree of the operator L minus n tilde with respect to the set U1 is -1. Moreover, every solution of P tilde belonging to the boundary of U2 and U3 belongs also to the strip. And then is also solution of P. And we will say why in a moment. But take this for granted. The correct explanation is at last. So the degree of the same operator with respect to U1, U2, and U3, if none of this solution exists, is -1. So by the exclusion property, we can calculate the degree of L minus n tilde of U4. It can be calculated as the difference between the degree of the same operator with respect to U1 minus the sum of the other two of the same operator with respect to the other two sets U2 and U3, finding -1 minus -1 plus -1 -2 -1 minus -2 1. Then we have found the solution of P tilde. But this solution belongs to U4, and U4 belongs is contained in the strip. But the a priori bound we have proved before guaranteed, again, as in the previous theorem, that the solution, that the problem has not been modified outside, has not been modified in the strip. So finding a solution on the strip guarantees that the problem has a solution that belongs to the region where the problem has not been modified. So this is nothing but the solution of P. To conclude, here is the idea of the calculation of the degree. For simplicity, I have omitted the operator and I left only the sets. So the degree on the entire square, limited by the two pieces of lines, red and blue, is -1, and it is U1. The two sets U2 and U3 are contained in U1, and the degree is -1. And by exclusion, we have that the degree of U4 is +1. To conclude, only two remarks, some application of this theorem. And for this problem and for this theorem, we have two main applications, the P Laplacian and the mean curvature operator. Both of these problems that reads as in this form or in the second form can be by a suitable position be rewritten to be equivalent to P. The first, for example, it's sufficient to choose f of t, x, and y to be y in absolute value to the power q minus 2 times y, and automatically g to be taken as h of tx and y to the power q minus 2 and y. And this can be easily seen if you remember the slide where I have talked about the invertible homeomorphism phi. This is the case. With this, only some further development. We have not already seen known of this. We have these are problems that can be studied after this. It's possible to consider other boundary value problems like Dirichlet, Neumann, Sturm-Liouville. Another way to consider a generalization of this theorem is to generalize it to system of order 2n, and maybe as done in the previous article, but for other kind of system, why not infinite dimensional problems? But this is very far at the moment. And with this, I have really concluded. I only leave you with the references to our article, that is the second, and the first article, that is an article by Professor Fonda and Professor Rodica Toader, that give us the main ideas and develop the first idea and the most important points that allows us to generalize the result here presented to well-ordered and non-well-ordered case for periodic planar systems. So with this, I have concluded. I thank you all for the attention, and to the next AJS. Thank you to everybody, and goodbye.
Thank you a lot, Giuliano, for your seminar. Okay, now it's a moment for questions. If somebody has a question, he can write or unmute himself. That's to Giuliano. Okay, so it seems that there are no questions. So I propose to thank Giuliano again for his seminar, and we meet as usual on next Friday. Thank you all, and thank you, Giuliano, for your seminar. Thank you.
Thank you to everybody. Bye.